Hello, Wellesley High School. Today we're going to talk about potential energy diagrams. The first thing we need to do is label our axes. The y-axis is going to be potential energy, and the x-axis is extent of reaction. These diagrams allow us to compare the relative energy of the reactants to the energy of the products in order to know whether the reaction is endothermic or exothermic. Remember that exothermic means energy is released, and endothermic means that energy is absorbed. Let's look at an example. In this example, the reactants have a higher potential energy than the products. That means that this reaction is exothermic. Energy is released when you go from the reactants to the products. The products are lower in energy than the reactants. There are a couple important details on this chart that I'll put in and label. The first is the magnitude of delta H, okay, the enthalpy of the reaction. And the second is the activation energy. So basically the energy barrier that the system needs to overcome in order for the reaction to happen. Okay, I've labeled the delta H in blue. That's basically the energy difference between the reactants and the products. In this case, the sign on delta H would be negative because the products are lower in energy than the reactants, and so energy is released. I labeled the activation energy in red. Okay, that's again the energy barrier the system needs to get over in order for the reaction to happen. At the top of that hump, at the top of the activation energy, is the activated complex. The activated complex is a sort of in-between state where the bonds in the reactants are starting to be broken and the bonds in the products are starting to be formed. Okay, so the activated complex is sort of this in-between state at the top of the energy diagram. It's a high energy state because of all the partial bonds. We've been looking at an exothermic reaction. Let's go ahead and look at an endothermic reaction. Okay, this is a potential energy diagram for an endothermic reaction. Notice here the products are higher in energy than the reactants. Okay. Let's go ahead and label our delta H and our activation energy. Okay, so our activation energy and delta H are labeled. In this case, the delta H is going to be positive because we have an endothermic reaction. Heat has to go in to make the reaction happen. And notice the activation energy has a larger magnitude than in the last one. This isn't always the case, though, for an endothermic reaction. Just happens to be the one that I drew. And then remember that the activated complex is still going to be at the top of the hump. Okay, and again, that's going to be the in-between state between the reactants and the products. Some bonds being broken and some bonds being made.